All right, so anybody can look up on Wikipedia what the electron transport chain is. Ultimately, this is going to explain what happens to NADH and FADH2. It's going to explain where the electrons in those molecules go to. Ultimately, they get accepted by oxygen, which is the explanation for why you're breathing. Fortunately, though this process is very difficult to understand, you don't have to think about it to have it happen. You're going to be breathing the whole time, and you're not going to be thinking about breathing, except now you are. Your mitochondria are going to be toiling away all along to do this. You can understand the electron transport chain at many levels. One is this cartoon level. And we joked last time, you know, would it be a question on the exam, fill in the numbers from 1 to 4? Can you count? In some ways, it's simple. NADH and FADH2 deliver electrons to complexes 1 and 2 respectively. Then those electrons get delivered to a carrier, which is called coenzyme Q. That delivers electrons to complex 3, which delivers electrons to cytochrome C, which shuttles over here to complex 4, delivering them to complex 4, which ultimately delivers the electrons to oxygen and makes water. So this is a protein-based wire for electrons. Now, along the way, some of these complexes, while they are transferring electrons, they take hydrogen ions and move them from one side of the membrane to the other. This is the inner mitochondrial matrix, the space inside the inner mitochondrial membrane, and then this is the space between that inner membrane and the outer membrane of mitochondria. And as electrons get transferred, these complexes are proton pumps. They are constantly pumping protons powered by the transfer of electrons from the inside to the outside. That creates what's called a proton gradient or a proton motive force. In science overall, anytime there's a high concentration of something over here and a low concentration of something over here, there's a driving force to move from a place that's high concentration to low concentration. And that's what the electron transport chain creates. You're storing proton motive force as you increase the concentration of protons up on this side. Eventually, at the end of what we talk about today, we will see how those protons mostly can't get back through the membrane except through something called an ATP synthase. There's a little channel in the ATP synthase that the proton can travel through back inside to the area where it's lower in concentration. As they do, they basically turn a crank that in a machine that synthesizes ATP. It's very rare that the way proteins work is analogous to the way we might see machines working. ATP synthase is one of these. There's actually something that rotates around, and it's that mechanical motion that actually makes ATP. So we're going to talk about all of that. At this point, we could sort of stop, and you would have enough of the gist of the electron transport chain that you could at least feel confident as you continue breathing that there's something going on down there that makes things breathe, that allows you to convert NADH and FADH2 into ATP. But I've always been uncomfortable with a cartoon view of things. I've always wanted to know what the atoms are doing, and maybe that's just because I'm a chemist. But nature is like perhaps a Russian nesting doll where there's always more to be understood at a deeper level. Or if you like the Cosmere of Brandon Sanderson, Kelsier says there's always another secret to be discovered. That one's not landing with, I think, anybody. Okay, that's all right. In a class of 250, there would have been like 2 people that are into Brandon Sanderson stuff, which I am. I think it's cool. I did press record, didn't I? All right, I was scared. Anyway, I've always wanted to know a little bit more about what the atoms are doing. And I admit that at some point you got to just stop caring, because if you zoom in too close, it may be too complicated for us to understand now. But we're going to zoom in a little bit and try to understand what some of the atoms are doing here. I'll have to tell you that I hope this isn't self-indulgent. It probably is, because I want to understand it at this level. If you want to understand it solely at the level that's in the quiz, that's okay. But I want to show you the atoms so at least you can be like, whoa, that's kind of cool, even though I don't quite understand it. That's kind of our goal for today. And if you do understand some of it along the way, more power to you. I don't think I can teach a class about this and be okay with myself if I don't show you what the atoms are doing. So, you okay with that? Go ahead.
Are we just going to need to know at the level of the quiz?
At the level of the quiz is, I think, as far as we're going to go for the exam, though for some molecules like NADH, FADH2, and coenzyme Q, I feel like you ought to be familiar enough with the structures of them that you could answer some questions about them. Okay, well, let's dig in. First, complex 1. We started talking about this last time. Here is a sort of cartoon of complex 1 that shows you, in most cases, not what the atoms are doing. This is a ribbon diagram of a protein, and we'll talk about these later. Complex 1 has an arm that faces the mitochondrial matrix, and then an arm that's embedded in the membrane. We talked last time about how you would expect the amino acids that are embedded in the membrane to be mostly nonpolar, whereas the amino acids that are in the peripheral arm, you'd expect at least some of them, the ones that are exposed to water, to be polar. So this end of the molecule is the one that does the electron transporting, and this end of the molecule is the one that does the proton pumping. So we're going to talk about those two separately, electron transporting and proton pumping. And if you can understand what's going on in complex 2, then what's going on in complex 1, then what's going on in complex 2 is going to be a little bit easier. So we're going to go through these things one by one to figure out what's going on, but let's do the overview first. NADH is going to deliver H minus, or a hydrogen and 2 electrons, to FMN, which is flavin mononucleotide. And I'll show you that. I think I showed you that structure yesterday. I'll show it to you again. In the process, NADH becomes NAD+, and now it's free and ready to go back and help out with glycolysis in the citric acid cycle. Its job is done. Its 2 electrons have been delivered. So this process delivers 2 electrons to the electron transport chain. So how come it says just 1 electron from here on out? It turns out that FMNH2, which is the reduced form, the one that has 2 electrons, can deliver those electrons one by one to the other elements of the electron transport chain. That's weird. We've never seen anything do that before. Most of the stuff we've done this semester has involved 2 electrons. So this is going to be a little bit unusual, and it's okay if you don't have an intuitive feel for why it happens. Single electron transfer is really like a high energy electron on one molecule, spreads out like a wave, and then jumps over to the other molecule. And this comes from the wave-like properties of electrons, and the maximum distance between things that can tolerate this kind of electron transfer is about 14 angstroms. So that's about the space between these two things here. In fact, these are a little bit closer. If you measure the distances between individual places where the electrons hop, they're all within 14 angstroms. So this single electron transfer is really a high energy electron on one molecule spreading out and jumping over to the other. That process is called tunneling. If you ever take a physics class, you might learn more about that, and that's sort of all I have to say about it. Where are the electrons going from FMNH2? They're going to these little box-like structures, which is how this cartoon is representing what is called an iron-sulfur cluster. The sulfurs are there to hold on to the iron atoms, iron ions, and the iron ions in these clusters are either in the +3 or +4 oxidation state. And iron that's in +3 can accept an electron to become +2. So as these electrons hop from FMNH2 to an iron sulfur cluster, one of the irons in that cluster is getting reduced from +3 to +2. And then it's going to trade that electron with another iron sulfur cluster, and so on. Hop, 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 hop. What's the driving force for those individual hops? Well, there's something called reduction potential, which you might have learned about, probably not in your general chemistry class. If you decide you love chemistry and you're like, dude, I gotta go back and take like 105 and 106, or I really wanna take Chem 111, you'd learn more about it. I'm seeing some angry shakes of the head on that one, so I'll shut up about that. Reduction potential basically says how energetically favorable is it for an electron to hop from one place to another. And people have likened this process of hopping to be like a roller coaster. Sometimes it's a little bit uphill in energy, and then the next one's even more downhill in energy. Ultimately, downhill in energy for the electrons to be delivered one at a time to a molecule called coenzyme Q, or another name for coenzyme Q is ubiquinone. Oh shoot, I need to duplicate this actually so I don't ruin the handout with my notes. We need an authentic copy. Where did it go? Oh well. There it is. All right. Nope, that's not the one. Ooh, and that was the wrong one I copied. Sorry, folks. Duplicate. There we are. Okay. I'll show you the structure of coenzyme Q. Ultimately, coenzyme Q gets reduced. It receives 2 electrons from this iron sulfur cluster, one at a time, and then it gets protonated twice and becomes the reduced form, which is called ubiquinol. And I'll show you the structure. This is an interesting structure because it stays inside the membrane and diffuses within the membrane, but it never goes outside the membrane. At that point, complex 1 is done. Coenzyme Q is going to be the electron delivery boy for the next complex. But the process of electrons trickling down from one iron sulfur cluster to another changes the shape of the membrane arm, and it allows protons to be pumped from one side to the other. And I'm going to show you how that happens. It's really kind of cool, and it basically relies on changes in pKa's of various acids of polar groups that are at the membrane or embedded inside the membrane. Okay, that's your overview. Go ahead.
Just before we continue, I just want to make sure I'm understanding this right. So the electron transport starts with NADH.
Yep.
And then how does it lose 2 electrons?
I'll show you that. You want to see it? How does NADH lose 2 electrons? So this is NADH, and this is the receiver of electrons from NADH. It's called FMN, or flavin mononucleotide. This hydrogen with its 2 electrons gets transferred to FMN. I don't think you've seen NADH be a hydride deliverer before. Mostly what we've seen has been NAD plus accepting a hydride. What we're doing now is exactly backwards. Recall that when NAD plus accepts a hydride, the hydride comes here, these electrons kick here, and these go there. The reverse happens when a hydride is delivered. So lone pair electrons on the nitrogen kick here to form a pi bond. These come here to form another pi bond. If we stop there, we'd have 5 bonds to carbon. H minus is the leaving group. And you can think of H minus effectively as hydrogen H plus, a proton, plus 2 electrons. So those are the 2 electrons being delivered from NADH to FMN. The hydride with its 2 electrons comes here, then these electrons kick here and these pick up a proton. Ultimately you end up with NAD plus and FMNH2. Follow-up question.
How does the H minus become H plus?
It doesn't, it's, I should have put air quotes here, it doesn't become that, but you can think of it, you were wondering where the 2 electrons are, they're carried in H minus.
Okay, so it's like the 2 dots, and then once it, you could see it as just H plus the
Right,
2.
it's never, in this process, it's never hydrogen plus and 2 electrons. But an H minus is the equivalent of a hydrogen and 2 electrons. Yeah.
I understand what you're saying about like how it looks in comparison to the cartoon, just like which is the inside, which is the outside, hydrophilic and phobic. But could you help us visualize that a little bit better, like in comparison to the cartoon?
Okay. So let's see, the mitochondrial matrix is water. The outside the membrane, the intermembrane space, is also water. So then the membrane is what we learned about earlier. You've got polar head groups that are exposed to water and enjoy being in water, or rather can interact with water. And then you have nonpolar tails, which cannot interact with water. And so, oops, nope, it's not. Sorry, I'm gonna try. So the space that's marked out in gray is full of these things.
And so is the peripheral arm, is that on the side with the hydrophilic side?
Oh, sorry. So
I guess I'm saying, like, when you look, if you're comparing this to that first image you have at the top.
yeah,
And you're
this is
comparing-
upside down relative to the image on the bottom,
Yeah.
and I couldn't correct it without causing trouble. But we can do so here. That may or may not help. But so I think you're getting 2 things mixed up. What I said is the membrane is nonpolar, but has polar head groups. This side, the mitochondrial matrix, has fewer protons. This side, the intermembrane space, has more protons, and they get pumped in this direction from, as we've drawn it here, top to bottom. Is that all right?
Yeah, that makes more sense.
Yeah. Sorry, I guess this is what I get from lifting stuff from Wikipedia. We could have done better, but what do you got? What are you gonna do? Okay. All right, other questions? Yeah.
So before we had talked about H plus being really terrible, or H minus being really terrible cheeseburger.
Yep.
Would this be kind of an exception because of the reaction specifically?
So yeah, it's a great question. H minus is a really terrible leaving group, and how does this happen? The answer is likely that NADH and FMN come close enough that it's just a direct handoff. H minus never has to float away and get in water. If it did, you'd make hydrogen gas, which would be a problem. Instead, it's just a direct handoff. Here you go. And and in that case, because H minus is never really on its own, it can work. All right. Others? Other questions about delivery of 2 electrons to FMNH2? All right. Now we need to talk iron sulfur clusters before we talk about how FMNH2 transfers electrons one at a time to an iron sulfur cluster. Some of this is going to be some of what's written in your handout is too much. As you can see from the quiz, you're never actually going to draw an iron sulfur cluster. But I want you to see what the atoms are just so it's less mysterious to you. So here are 2 kinds of iron sulfur clusters. If you don't care, don't worry about it, but they both have an overall -2 charge. 2 of the irons in the iron sulfur cluster it's this cube, 2 of them are in the iron +3 oxidation state, and the other 2 are in the iron +2 oxidation state. And remember, it's the iron 3s that are going to receive an electron in the electron transport chain. Some of them look like this, cube structure. Some of them look like this, sort of square structure, with 2 iron 3s. Okay? And again, it's the iron 3s that can be converted into iron 2 by receiving an electron. What are these random sulfurs? Those are sulfur atoms. It's just a sulfur surrounded by 8 electrons. And that would have a 2- formal charge. Where do those come from? I don't know. Biology makes them. I got nothing. If you want to know more about it, we can look it up. But I probably am not interested. Isn't that sad? Even I'd stop caring at a certain point. These other sulfurs come from amino acid side chains. CYS stands for, that's the 3-letter code for the amino acid cysteine. This is a sulfur-containing amino acid that you will learn about later. And by later, I mean probably tomorrow. But these cysteine side chains are an anchor for the cube in the protein. And the overall charge is 2-. If it were to accept an electron, one of the irons would go to 2+ instead of 3+, and the overall charge would be 3-, because that's what it means to accept an electron. Okay, any questions about that? Where's the electron going? It's going into one of the d orbitals on iron. Iron is a Lewis acid. It has some empty d orbitals that can accept electrons. So that's an iron sulfur cluster, and it's just a way station for an electron to be transferred. And here's just an illustration of what I said in words, not a big deal, but this iron sulfur cluster where 2 irons are at 3+ and 2 are at 2+, takes an electron from somewhere, some electron donor, and the iron in the lower right-hand corner went from 3+ to 2+. Okay, and so the iron sulfur complex got reduced. Over to the right is an example of how that might happen with this sort of square-shaped complex. Questions about that? You can think of these as iron sulfur boxes for holding electrons, and that's not actually that bad of a way to think about it. Okay. So notice a couple of things. First, NADH transferred basically 2 electrons at once. The oxidation of NADH by FMN, we're going to call that a 2-electron process because 2 electrons were transferred at the same time. Unfortunately, the iron sulfur clusters do only 1-electron processes. They can only transfer electrons 1 at a time. So this is why NADH can't give its electrons to the iron sulfur cluster directly, but it needs the intermediary of FMN. Because FMN is very versatile. It can accept 2 electrons at once. It can give away 2 electrons at once, but it can also do single electron chemistry. So if you've ever traveled to Europe from the United States, you need an adapter to plug your phone charger or computer cable into the wall, right? And you need a different adapter in the UK than you need in Europe. And in the same way, you need an adapter so that NADH can transfer its electrons to the iron sulfur chain. And FMN is that 2 electron, 1 electron adapter. So that's an important point that would be good for you to know, that the FMN and FAD are good at single electron transfer. So it sort of acts as an adapter between NADH and the electron transport chain, and the iron sulfur cluster. Okay, so here's how FMN can donate electrons to an iron sulfur cluster. The abbreviation here, SET, stands for single electron transfer. That's the thing I was talking about, where the electron is a wave, it spreads out, and as long as the next place is within 14 angstroms, it can hop. Okay? The electron that hops, unsurprisingly, is one of the lone pairs on nitrogen. If you were to look at this molecule and see all of the lone pairs that are in it and all of the carbon and oxygen pi bonds, you'd make the conclusion that the lone pairs, one of them at least, would be the high energy electrons in the molecule. Moreover, if you knew about nitrogen being less electronegative than oxygen, it would be a pretty easy jump to say, well, I bet you the electrons are on nitrogen are higher in energy than they are on oxygen. Because that's literally what electronegativity means. Atoms that are more electronegative, their electrons are lower in energy. So it shouldn't be too much of a jump or a surprise that the electrons on one of these nitrogens are high enough in energy to do the single electron transfer. As to why it's only one of those on that nitrogen instead of the other nitrogens, I don't know. I got nothing. It doesn't actually matter because the whole system is conjugated anyway. But that's a story for another time. So it's tough to draw arrows for single electron transfer. Usually when we draw arrows for 2 electrons, the arrow on the end has 2 little flags at the end. If you only have 1 little flag, that means 1 electron. Normally when we have an arrow point from an electron to another atom, that indicates that a bond is forming. In this case, with single electron transfer, we're not forming a bond. The electron is hopping from one place to another. Okay? So we're going to take an electron from FMNH2 and have it hop onto this particular iron 3+ in the iron sulfur cluster. I said the word hopping, and suddenly I'm back to the 1980s in Sesame Street when they did a song called The Caribbean Amphibian. You should look it up because nobody knows that one. Well, he's a Caribbean amphibian. I think they had Jimmy Buffett visit and sing that. It was kind of fun. Yeah, go ahead.
So you said it doesn't matter which electron on what, whichever nitrogen.
Right.
And then does it also matter for which iron 3 it goes to?
That's right. We won't know which iron 3 it goes to. So I am not going to ask a question where I show you one of these is correct and I draw arrows coming from different electrons on different nitrogens and going to different irons. Yeah, this is just an example of what might happen. Now notice here I've labeled this iron sulfur cluster N3. That's the one that is closest to FMN, so that's the one that has to take the electron from FMN. The others are all too far away. So it's interesting, isn't it, that there's this fundamental physical limitation on how far electrons can hop, and nature puts boxes for them to hop into all along the path. There's a path prepared. Okay. Electrons stick to the covenant path too. How's that for spiritually inspiring? I don't know. All right, go ahead.
What do you mean the other ones that you borrowed?
So if you go back and look at that cartoon on the first page, and I realize the print is really small, so just I'm zooming in and look at it here. This complex N3 is pretty close to this green thing, which is the FMN. That's where FMN is. FMN can only transfer its electrons here. It can't here or here because those are too far away. All right. So once FMN has done that, the iron sulfur cluster gets reduced. This iron that used to be iron 3 is now iron 2. The charge on the cluster increased. This is what you're left with. You steal one electron and one electron only for FMN. You get something that's called a radical cation. It's now positively charged. That becomes acidic, and nature deprotonates it to give you this FMNH, which is a neutral radical. It's still, a radical is an unpaired electron. If you've ever heard about people talking about free radicals in biology, they're talking about molecules with unpaired electrons. They tend to be pretty reactive. So at this point, when one electron has been transferred to the iron sulfur cluster N3, then that iron sulfur cluster can donate an electron to the next one down the line. This is what that might look like. This is N3, this is N1B. N3 is reduced. Its iron, which used to be iron 3, is here iron 2. We're going to do a single electron transport hopping to the nearby iron sulfur cluster N1B, and now this one is going to become iron 2. So hop, and then another hop. And so that electron will continue hopping down those iron sulfur clusters until it gets to the bottom. Yeah?
So this probably seems really obvious, but I'm just here for me. So when the electron hops to the F3, then it becomes an F2, and then hops to the next F3, which turns into
Right. Once it's, when the electron hops from F2 over here to F3 over here, then this one becomes F3
Why does it go to the next one and not to the other F3 that's
in the same cluster. It might. It's probably, before it does this big jump, it maybe is hopping around between irons like crazy. So the iron sulfur cluster, each iron sulfur cluster itself is a box that contains the electrons. Within that box, I hadn't actually thought about it till you said it, but it makes sense that an electron ought to be able to hop back and forth from one iron 3 to an iron, from an iron 2 to an iron 3 and so on. That's not what you were asking, is it?
No, it was.
Okay. Yeah, so think about the, within an iron sulfur cluster, think about an electron hopping from an iron 2 to an iron 3 and therefore switching oxidation states. Think about that as bouncing around inside the box like crazy, and that happens and you can't tell it's happening, and then occasionally you'll fly out of the box and hop to the next one. Cool. All right. So you've sort of seen how this is happening. We talked about an electron transfer from FN1 to N3 to N1B and so on. It's hopping from one box to another, all within that distance limitation that we talked about. Let me show you the second electron transfer from FMN. This is the FMNH. It's gotten rid of one electron from FMNH2, but now it needs to deliver the second one so that it can receive, so that it's ready to go again with another molecule of NADH. The second electron transfer happens from this other nitrogen, again hopping from this molecule to turn an iron 3 into iron 2. The N3 box gets reduced so that the iron 3 becomes iron 2. Now you get another radical cation that gets deprotonated. Once it's deprotonated, the lone pair electron on this nitrogen and the lone pair electron on that nitrogen can actually recombine to give you, oh, there's a mistake, FMN again. Okay? Nope, that's a terrible, all of it's a terrible mistake. Let me try that again. You may need to correct this structure, FMN. All right. So we've talked about FMN delivering its electrons one by one. The nuances of the FMNH radical cation and then getting deprotonated, that stuff I'm not going to ask you about. It's there if you want to pay attention to what's going on and how the electron transfer happens one by one. It's enough for you to remember that FMNH2 is able to donate electrons to the nearby iron sulfur cluster one at a time. Yeah.
Would it be wrong to show it as like enzyme B going to the hydrogen and then nitrogen and then it going over to the iron instead of the...
Yeah, that is a fantastic question. Which happens first, electron transfer or deprotonation? And I don't know. The material I was looking at suggested it was loss of electron first, but certainly the other way sounds reasonable too. Yeah, others? Okay, so let's get to the bottom of the chain. This is the part where an electron is going to be transferred from the box iron sulfur cluster N2 to the receiver ubiquinone. So we need to draw the structure of ubiquinone, which is in your handout, and that's here. So this is ubiquinone. I had to abbreviate this portion of ubiquinone because it would have taken across the whole page to draw it. There are 5 carbons in here, 1, 2, 3, 4, and 5, and those repeat 9 times. So it's a 50 carbon, and then you get the one on the end. So this is a 50 carbon tail, very long, very nonpolar, and that is the anchor, nonpolar anchor, that keeps this molecule, which we call coenzyme Q or ubiquinone, in the membrane. That's important because coenzyme Q needs to stay on task. It's a shuttler of electrons. It needs to not diffuse away into the mitochondrial matrix or into the intermembrane space. And so this anchor keeps it moving back and forward along the membrane and nowhere else. All right, so the structure of ubiquinone is this. You've got a 6-membered ring, some pi bonds, and 2 ketones. There are empty orbitals in this molecule. We won't talk about the MO theory of that molecule, but just for now, think about there are antibonding orbitals that are relatively low in energy, and they can easily accept an electron. So, again, single electron transfer, electron hopping from an iron 2 in the reduced form of iron sulfur cluster N2 jumps to one of the carbons in ubiquinone. I'm showing you one option. You could imagine others. That will you're partially populating an antibonding orbital, and it's easiest to draw the structure that results as follows. The electron gets donated to this carbon. These shift over to form a pi bond here, and then these shift over to pick up a proton from some acidic source. And you end up with this neutral molecule. In other words, you delivered in this reaction 1 electron and then 1 proton in the same step. So the overall charge didn't change, it stayed neutral. This is the, so that is a 1 electron process. This is the halfway point, that's why they call it a semiquinone, and then it's going to receive another electron from another cycle from reduced N3 iron sulfur cluster, and then it's going to receive it with this other unpaired electron. Then electrons will kick down, will pick up a proton, again delivery of 1 electron and 1 hydrogen atom. And that gives you the reduced form, which is called coenzyme QH2 or ubiquinol. So you can tell that a reduction has happened because if you look at CoQ, ubiquinone, there are 2 ketones. And if you look at ubiquinol, there are 2 alcohols. Yeah, go ahead. Answer then, Kimberly.
Does the process basically for N3 just keep occurring until we get to N2 and we have to add in ubiquinone?
Yes. So FMN donates electrons one at a time. They fall down the chain individually till they get to the N2 box. And then from the N2 box, 1 electron hops over to coenzyme Q to make the semiquinone. And then that semiquinone stays there until another electron has fallen down from FMN H2 to the N2 box. And then it hops over to the semiquinone to make the fully reduced ubiquinol.
So
The what process? The hopping from one to the other?
Yeah.
Yes. And there may be more than 5 steps there. I didn't actually count them. Yep. So FMN donates 1 electron. We're playing electron plinko here. Ding, 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 to coenzyme Q, and then another one. And when those 2 things happen twice, then coenzyme Q is reduced to ubiquinol, which I showed you here. So, 2 important things about ubiquinone. It receives electrons 1 at a time, but it ultimately carries 2 electrons. And in addition, it is anchored to the nonpolar interior of the lipid bilayer. So it's not going anywhere. It can go left and right, front and back, but it can't go into the water. Yeah. Kimberly?
So is that kind of what the dot is? Is it's the 1 electron that's received, and that's why?
Yes.
I'm just a little confused how it can carry 2 electrons, but it only can receive 1 electron.
So the dot on this carbon represents the 1 electron that was delivered from the iron sulfur cluster. Yep. And then that one has a space for another electron, which it receives here, and that's why afterwards there are 2 dots.
So it's kind of like just a 2-step process.
Uh-huh. Yep. Reduction of CoQ is a 2-step process, 1 electron at a time. Yeah.
I'm so sorry. I don't know if I'm like just missing something, but okay. So you got the FMN, which carries the electron to N3, and then N3 carries its electron to N1B.
Yep.
Right.
And then N1, keep going, go ahead.
And then it just shows us back to NH.
Right, so maybe this is your question, I'm sorry, I interrupted. So you are right that I skipped and glossed over all of these transfers between sulfur clusters, because if I were to draw them out, they would look just exactly the same as I drew them out already. I would just change the labels on them. So yeah, I didn't show you N1B to N4 or N4 to N5 or N5 to N6, N6 to NB, or N6B to N2. But I did skip ahead to reduced N2 and show you how that delivers to CoQ. Is that your question?
Yeah, I guess just so that my mind can visualize it. Does N4, 5, and 6 all look like N3, and then NB6 look like N1B?
Yes. It looks like N4, 5, 6, 6B, and 2 are all cubic-like structures. N1B looks like that's the only one that we're worried about that has the sort of square structure. Go ahead.
So it can't receive 2 at once because there's not 2 separate chains. There's just the one. So it has to do electron, and it has to get it, and then it has to give another electron, right? It's from
2 separate chains of what?
There's not 2, so there's not multiple N2s. There's only one N2 that's able to give the electron.
That's right.
And it has to get another one and then give you.
Right. The iron sulfur clusters are such that they can accept 1 electron but not 2. It's too high in energy to have them accept 2. So the reason it has to happen 1 at a time is because each iron sulfur cluster can only do 1 at a time.
I guess I was thinking of it like it was like an enzyme where it can just accept a proton from wherever.
Mhm.
But I was thinking about it where I was expecting that there were more complexes that could just give up that electron, but
Okay.
one, right?
I mean, the membrane has multiple complexes in it, but each coenzyme Q is made only when bound to a single complex. And so it's got to take electrons 1 at a time from the
There's only
funnel
one path it can go.
with which it's currently docked. Yep. All right, others? Okay, yeah, go ahead.
Maybe I shouldn't just question the biology of it, but it seems weird that it's not just NADH going straight to the ubiquinone,
Uh-huh.
giving those two electrons if that's what happens eventually.
Yeah, so it seems like it's a great question. It seems like, wouldn't it be more efficient for NADH simply to donate 2 electrons to ubiquinone? And you could probably draw a mechanism, you could probably draw a mechanism that would show that. This transfer, the hopping of electrons though, is important. If you just did that, NADH to ubiquinone, you would miss the coupling with the proton transfer. The one thing we haven't talked about, we've dealt with all the reduction, but we haven't talked about what's going on here that's going to pump protons to the other side. The energy of these electrons falling downhill and ultimately here is what drives this portion of the molecule to let 4 hydrogen atoms through per 2 electrons. And that's energy storage. That's like charging a battery. Yep, good. So I want to talk just briefly about now the membrane anchored arm where the proton transfer happens. This is going to get a little hand wavy. We could be a little bit more direct in terms of what the atoms are doing here, but this will be enough. The membrane arm has alpha helices that span the membrane. And most of the amino acids in the alpha helices, and we'll talk about what an alpha helix is in a little bit tomorrow or the next day, but for right now, think of them as a spiral. And most of the amino acids that are in those spirals are going to be nonpolar, so they can interact with the nonpolar tails of the lipids in the membrane. Some, though, will be polar. And those few that are polar are going to make a channel that water can infiltrate. Go ahead.
Sorry, I feel like before I continue, for the reduced, okay, I guess it's back to the ubiquinone H, when it only has a singular H.
Yeah.
You have it showing that the N3 is what gives it the extra electron.
N2.
Down.
Down? Oh, error, thank you. Sorry about that. Man. Yep, that is a copy and paste error. Yep. And I'm never going to ask you, is that N2 or N3? That would be pointless.
So ubiquinone stays there until it becomes H2, and then it leaves.
That's right. The CoQH waits there until it becomes CoQH2. All right. So now the electrons have been transported. Those electrons trickling from one iron sulfur box to another create changes in the shape of the helices in this membrane arm. And I've drawn a cartoon that shows a couple of the helices and a channel in between them where water molecules are. And I'm going to erase these arrows for a minute just so you can see what it looks like without them. Here's an H3O plus ion on the matrix side. Here's a few water molecules and then a few polar side chains in the interior of this channel. Now this channel is narrow enough that water molecules don't really flow through at a very fast rate. They mostly stay where they are. And an individual hydrogen ion does also not swim through from one side to the other. Rather, there's a cascade of proton transfers, acid-base one after the other, that ultimately takes H3O plus that was on one side, deprotonates it, and then reprotonates a water on the other side. And that's how this membrane arm pumps a proton across. And it's driven by, as the electrons trickle down from one iron sulfur box to another, it's driven by changes in the shape of this membrane arm and perhaps even changes in the pKa's of various amino acid side chains. So this is more like a hypothesis or an example of what might be happening than what is actually happening. But you could imagine that the water molecule on the, I'm going to abbreviate the intermembrane space as IMS, and then this is the matrix side. You could imagine a water molecule on the intermembrane space deprotonating this water molecule, which deprotonates that carboxylic acid side chain, which deprotonates that water molecule, which deprotonates that amino acid side chain, which deprotonates this water molecule, which steals a proton from that one. And overall, the net effect afterwards is H3O plus used to be on this side of the membrane, now it's on that side of the membrane. Okay? I wanted to show you that just because I feel like when we talk about proton pumping, you get this idea that there's some little guy in there turning a crank and that a proton is going kapwing from one side to the other. Kapwing, that is a sound effect from Calvin and Hobbes. If you don't know Calvin and Hobbes, you should look it up. It's not a show, it's a comic strip. I know that that's an old medium. Anyway, but it's literally just proton transfer from one side to the other. Yeah?
How does it reset?
How does it reset? That's a good question. To reset, all it would need is a fresh molecule of H3O plus to move here. I don't know. That's a good question. If amino acid side chains are involved, you would think that it would need to reset. And I didn't think that far ahead, so I got nothing for you. Really, actually, so I'm going to need another page to show this. Copy. Nope, I didn't want copy. I wanted insert, add page. To show you this, I actually think after the proton is transferred, it doesn't need to reset. Let me show you why. So what we'll do is I'm going to redraw this, only I'm going to have to draw new protons where they now are versus where they used to be. So this is what it looks like immediately after. Notice that the two side chains in the middle are basically still at the same protonation state they were at before. They each still have one proton, and just by rotating, they could get in the right orientation to do it again.
Oh, that's yeah.
Yep. All you would need to reset is to have this one swim away. Sorry, I'm thinking Finding Nemo, swim away. And this one swim away, and then another H3O plus to come, and so on.
Okay, that makes sense.
Yep. Okay. All right. So overall, in complex 1, you get 2 electrons delivered by NADH. They're delivered first to FMN, then one by one, they get delivered from FMNH2 to the iron-sulfur cluster chain, ultimately being delivered one by one to coenzyme Q, which becomes ubiquinol or CoQH2. 2 electrons from NADH, 1 coenzyme Q reduced to CoQH2, and 4 protons translocated across the membrane. Yeah?
Just to confirm, those protons aren't going to go backwards because of what's happening on the arm, right?
Yeah, the protons aren't going to go backwards because of the relationship, which at this point is pretty hand-wavy as far as we're concerned, between the electron transport arm and then the membrane arm. But yeah, it won't run backwards. Some of these enzymes can run backwards under certain conditions, but we won't worry about that. Yes?
Maybe this is kind of just rephrasing what you said, but the ubiquinol, what makes this thing on the right happen? Proton transfer?
The proton, go ahead.
Happens 4 times for every ubiquinol that's created?
That's right. Yep, because you need 2 electrons to make ubiquinol, and presumably that trickling down of 2 electrons, each one causes 2 protons to be translocated. Yeah.
For an exam, would you like us to understand the mechanisms for all of these, like the iron sulfur clusters and stuff?
For an exam, do I want you to know the mechanisms for all of this? The single electron transfer from FMNH2 to an iron sulfur cluster? No, I'm not going to ask you to push arrows for that. I do want you to know that it happens one electron at a time. Same thing with making coenzyme Q. You've seen it now. I always felt when I was taking a biochemistry class that if nobody showed me the arrows or the atoms, I didn't really understand what was going on. I'm not going to ask you to reproduce this arrow pushing mechanism from reduced N2 to the coenzyme Q, but I do want you to know that it receives it one by one. All right, with that, go ahead.
Sorry, I'm just confused how after it becomes co-ubiquinol, or not co,
Yeah,
ubiquinol with the H2,
yeah.
how then does it lose those protons to then go through the
So what we'll talk about next is the fate of CoQH. All we've done is dealt with complex 1.
So then when does that chain happen where you were showing with the different waters?
Water.
Sorry, like scroll
The
back.
inner membrane.
The inner membrane, yeah.
Oh, sorry. The protons that get added to ubiquinol are different from the ones that get translocated across the membrane. Yeah. So as ubiquinone is reduced to ubiquinol, it happens one electron at a time. You get a negatively charged intermediate that's got to get protonated. Those protons have to come somewhere. They come from the mitochondrial matrix, but they don't count because there's no net change because CoQ cycles back from ubiquinone to ubiquinol as it's carrying its electrons from one place to the other. So get a few protons, lose a few protons. You'll see that as we connect the dots in the.
So it's two separate reactions.
That's right, two separate reactions. This one here with this proton is to combine with this electron to make ubiquinol. And then these are being pumped across the membrane.
Okay, that makes sense.
CoQH never leaves the membrane, and when it delivers its electrons, I think its protons get released. Anyway, yeah. Okay, other hands? No? Yeah?
So it gets its electrons from NADH, and for every 2 electrons it receives, it pumps out 4 protons?
Yep.
Okay.
All right, so that I think gives you enough to fill in the complex 1 column. We've gone through that in a lot of detail. Fortunately, we're not going to do that much detail for any of the other complexes, so I think the hard part is mostly over. Let's go ahead and take a break, and we'll pick it up with complex 2 in about 5 minutes.